In the previous video, we talked about momentum optimizer, and here we'll discuss AdaGrad. So, in different type of optimization algorithm. So, before starting, let's have a quick recap of vanilla gradient descent algorithm. So, we initialize the learning rate. We start with the first iteration, 0th iteration. We choose some random weights, and then we iterate until convergence. We compute the gradient of the error with respect to WT, that means the weights at that iteration. Then we'll update the weight parameters. WT plus 1 equals to WT minus alpha times gradient of the error. And after convergence, we get our optimal weight. So let's say this is one 3D curve of the loss graph. So this is our minimum point. In 3D, we can see it in this way, and if we just create a contour plot, and in 2D we can visualize it in this way. So similar color circles represent similar height points in the curve. Now we see one problem with in our vanilla gradient descent, and that is with the sparse features. So let's see one very simple example, house price prediction. So we have these features: size of house, number of rooms, age of building, and airports nearby or not. So you see this airport nearby or not, this is a very sparse features because very few house will be nearby airport, right? So most of the time the value will be 0 and very few times it will be 1. So this is a sparse feature. So their gradients are 0 or very small most of the time for this sparse features. So with a single global learning rate, this weights will receive very few updates because the gradients are 0 or small at a time. So the weight updates also will be very small, right? So it will change very slowly and get overshadowed by frequently updated weights. So if we are having multiple features, right? So this feature, its update will be very less. So it will get overshadowed by the frequently updated weights. So as a result, weights associated with sparse features fail to learn meaningful values. So let's see this 3D loss graph here. So here you see this is kind of like this, right? So in this direction we are moving towards the minimum, but in this direction you see there is not much change. So if you start from here, you will move in. If you start from here, you will move in this direction, but in this direction there is not much change. So you see this is the frequent parameter side and this is the sparse parameter side. Now consider a simple linear regression. Y hat equals to W0 plus W1x. So the loss function using Xylee mean squared error we can get, or squared error we can get y hat minus y whole square. Y height predicted output and y is actual output. So we get W0 plus W1x minus y whole square, this thing. So the gradient of this del E del W1 with respect to W1 will be what? 2 times this thing, and then we get x from this term, right? So similarly we'll calculate del E del W0 also, but I'm just considering del E del W1 here. So the gradient update considering only this W1 is WT plus 1 is WT minus alpha times del E del W1, right? So if x is sparse, then most of the time, so this will be 0 because we have x here, we are multiplying with x, right? So this del E del W1 most of the time it will be 0. So we are not deducting anything, right? So in most of the cases, WT plus 1 will be WT. So there will not be any gradient update, right, for this W1 side. So that's how, like, let's say this is the minimum point. Let's say you're starting from here. So this is the direction where we are having updates. This is the frequent parameter. So in this direction we'll move. Then here, after reaching here, in this direction you see will not have much update, right? So we might not reach the minimum point also. So the problems with sparse parameters is they don't learn. So you see this neural network scenario now. So Wt plus 1 is Wt minus alpha times g hat Wt, right? So g hat Wt is gradient of error with respect to Wt, error weight parameters at that iteration. So this g hat Wt, this is the gradient at this iteration t, that is basically for all the weights we have to calculate, right? So del E Wt, del W11, del E Wt, del W12 and all. So for all the weights. So in real life scenarios, we calculate it layer wise, but I am just showing it. We have to calculate this del E, del W11, del E, del W12 and all for all the weights. So we have to calculate, let's say del E, del W211. So using the chain rule of calculus, del E del W211, it will be del E del Z11 times del Z11 del W211, right? So what is Z11? Z11 is a linear combination of the previous layer, right? So let's say this is, we have one bias as well, W011, then W11 x1 plus W211 x2. This is Z11, right? So if we compute del E, so del Z11 del W211, this is what? Del W211 is here, so we get x2. So this term is x2. So what will be del E del W211? So if x2 is sparse variable, right? So in that case, in most of the time, we'll get del E del W211. This is will become 0 for most of the time as x2 is sparse. So it's the same problem. It can happen for simple scenarios as well, or deep neural network as well. Now, coming to the main idea of AdaGrad. So the main culprit here is the fixed learning rate. So why fixed learning rate fails? So earlier we had this, right? Wt plus 1 is Wt minus alpha times g hat of Wt, right? So we have a fixed learning rate. So same learning rate for all the void parameters. So this g hat Wt is a vector, right, in multiple directions. So we'll use same learning rate for all the parameters. So we'll have some parameters learn to first, but the others learn too slow for sparse features. So the main idea behind AdaGrad is, can we have different learning rates for different weights? So that means basically adaptive learning rates for gradient descent. So that's why we call it AdaGrad. So key intuition of AdaGrad is parameters with large gradients should get smaller learning rates, and parameter with small gradients should get large learning rates. So in case of momentum, what we did? In momentum, we are focusing on direction. So if we are moving in the same direction again and again in multiple iterations, so we'll take larger steps in that direction. In AdaGrad, we focus on the magnitude of the gradient, not the direction, right? So weights with large gradients should get smaller learning rates, and weights with small gradients should get larger learning rates. So that's the difference between momentum and AdaGrad here. So now this is the AdaGrad formulation. So RT plus 1 equals to RT plus G hat Wt dot product of G hat Wt. So this is element wise product. What is element wise product? So U dot product of V, this is element wise product. Let's say U is this n-dimensional vector U1, U2 till Un, and V is n-dimensional vector V1, V2 till Vn, right? So the dot product of U, V, the element wise product will be E1, V1, U2, V2 till Un, Vn. This is the element wise product. So if you compute G hat Wt dot G hat Wt, so it basically squares each element. So we are computing dot product with itself. So it will square each element. So we are ignoring the direction and just focusing on the magnitude. So in this different direction, in different for different parameters, we can have different directions. So few will be positive, few will be negatives, right? But when we are squaring, we are just ignoring the direction. We are just getting the magnitude. That too, we are squaring it. So we are getting much more amplification. And next, what we are doing is Wt plus 1 is Wt minus alpha times this delta plus root of this Rt plus 1, R power t plus 1 dot product of G hat Wt. We'll come to this later. First see this thing. Rt, this is one vector, right? R1, R2, this is one vector. G hat Wt is the gradient vector, right? G1, G2 and all. I have written it very simply. Rt plus 1 will be, this is also element wise operation. So for each element it will be R1 plus G1 times G1, R2 plus G2 times G2 and so on. So all these are element wise operations. So now here Rt is squared gradient accumulator, it's a vector, and square root of Rt is basically what? It's the element wise square root of Rt. So if Rt is one vector, right? So square root of Rt is square root of each element in that vector, right? So we'll get a different vector where each element is the square root of each element in the Rt. Delta, this is an hyperparameter for stability. We'll see why we need it. So in the original gradient descent, we had this, right? Wt plus 1 equals to Wt minus alpha times G hat of Wt, right? So in place of delta alpha, we get alpha divided by this delta plus this root or square root of Rt plus 1. So let's say we don't have this delta. But in that case, this Rt plus 1 can become 0 anytime, right? So we'll get divide by 0 error in that case. So that's why for stability, we are adding this delta term. So this is one hyperparameter. And then also this is also element wise dot product. So let's say 1 over this square root of R powered t plus 1. So this is, let's say this vector, right? 1 over square root of R1, 1 over square root of R2 and on, right? So this 1 over this delta plus this thing square root of this RT plus 1, this will be 1 over delta plus square root of R1, 1 over delta plus square root of R2, right? So this things is becoming one vector, alpha times alpha over this delta plus square root of RT plus 1, this will be this vector. This is becoming a vector now, right? So earlier it was a scalar value, but here now we are getting a vector. So that's why we are doing a element wise product with gradient. So now let's see, let's say this is some values we assumed, and alpha over del plus this square root 1, this is this one, let's say, and we are just doing this element wise dot product, right? So it will be alpha over del plus this square root thing times z1 for the first item for first row, and similarly alpha over del plus square root over 2 this times z2, and this way. Earlier we had same learning rate alpha for all gradient elements. So now for different gradient elements we have different learning rates. So that's the advantage of AdaGrad. Now if we haven't seen zeros much for some weight entry, so we have not seen zeros much, right? So this squared gradient accumulator will go up, right? So we have not seen for non-zero, non-sparse elements, basically this will go up. Then alpha over this del plus square root of this RT plus 1, this will go down because we are dividing by this, right? So this will go down for that weight. So we'll take smaller step for that. So weights having more updates, non-sparse features basically, will take smaller step size for that. So that's like the more it learns, the more cautious it becomes. If we have seen lots of zeros for some weight entry, let's say for the sparse features, then this will become slow or with zeros most of the time. So the squared gradient accumulator, this will be very small, and then alpha over this alpha divided by this del plus square root of this thing, it will be very large for that weight, right? So if it is large, so we'll take larger step for that weight. So weights having less updates will take larger step size for that weight. So large updates for sparse features, otherwise they won't learn. Now one question comes to our mind is accumulated squared gradients. In this case we are taking squared gradients, and then again we are taking square root here. Why we are doing that, right? Let's see this. So in this case, when we are taking this squared element wise product here, this will always have positive entries. So it is basically we are focusing on magnitude, not the direction. We are just ignoring the direction, we are just focusing on the magnitude. So it cares about how big updates were, not their sign. Whether it's positive, negative, it doesn't care. And then we are taking square root. So AdaGrad squares gradients to track magnitude and takes square root to control the scale. So and adds this delta, we already told, right? This is for numerical stability to avoid the divide by 0 error. Now see the limitations of AdaGrad. So aggressive learning rate decay. So this is one limitations of AdaGrad. So for weights having many updates, this RT only increases as we are taking squared gradient. So for the few weights, those are non-sparse features, right? So we'll have many updates, right? This RT plus 1 will increase a lot, right? So that means this term will decrease a lot. It will be 10 to 0 almost, right? So effective learning rate for those weights will become 0 or close to 0. So in that case, eventually weight updates become negligibly small. So maybe it will not even converge. So if we don't have sparse features, if we have non-sparse features, for those weights, the learning rate will become very 0 after some point, and it will stop learning. So that is the main limitations of AdaGrad. Strength is it handles sparse data very well. No manual learning rate tuning. So automatically we will have multiple learning rates for multiple features, and it is useful for NLP and text features. In AdaGrad is excellent for sparse and high dimensional data. Update varies for non-sparse features will have more update, so we'll take small steps. For sparse features will have less update, will take larger steps. So learning slows over time, of course. The more it learns, the more cautious it becomes. The key problem with AdaGrad is learning rate decays too fast. The training may stop early. So though AdaGrad comes with a very intuitive approach, so different learning rates for different features, right? Different weight parameters. So it tries to solve this main basic problem of fixed learning rate, but still it sees learning rate decays problem for non-sparse weights basically, and non-sparse features basically, and training may not converge. So that is one limitation we have with AdaGrad that we'll try to solve in our next optimizer called RMSProp.